Okay, engineers, on this video we are going to see the demonstration of the convolution theorem. The convolution theorem says that the Laplace transform of a function convolution with another function is simple in the S domain, the multiplication of the Laplace transform of each one of them. Alright? In the previous video we saw an example that actually happens, but we have to prove that it happens for all convolutions. Okay. To start, this is going to be a very long problem, so I'm going to try to use as much space as possible. So I'm going to write small. So let's start with the definition of the f of s. The f of s is the Laplace transform of f of t. With this is the definition. The only thing that I change here is that instead of being t, I change it by tau. So exponential minus s tau, f of tau, differential of tau. There is no change because the result is a function of s. So it doesn't matter if you have t or tau or whatever. On the g of s, we also use the Laplace transform definition, but I changed the t by beta. Why different variables? Because I'm going to make the combination. Okay, now. So what the way we are going to prove that is from the right to the left, meaning from here to here. So let's do the multiplication of f of s times g of s. Okay, so let's start. F of s times g of s is equal to the integral from 0 to infinite exponential minus s tau, f of tau, differential of tau, times integral from 0 to infinite exponential minus s beta, g of beta, differential of beta. Okay, now let's write these two integrals like this. Integral from 0 to infinite, and then f of tau, and then integral from 0 to infinite. I'm going to bring this inside, so I'm going to make exponential times this exponential, because it's the same exponential. It's going to be minus s times tau plus beta, and then g of beta, differential of beta, and then differential of tau. So what you have here is two integrals, right? Okay, so but here I place it first the differential of beta and then the differential of tau. So that is why I have here outside of this integral, because this integral is respect to the beta, and then f of tau is a constant. Alright? Okay, now this is 2 by 2 integral. So you have here here you have tau, and here you have beta. No, sorry, you have here tau, and then you have here beta. Okay, what really matters here is the integration region. So for beta is from 0 to infinite, and then for tau from 0 to infinite, which is the other axis. So this is the integration region. Okay, so that is the integration region. Okay, so what I'm going to do is a variable change here. I'm going to do t equal to tau plus beta. Now on this integral, I'm going to make the variable change on this integral, alright? Because on this integral, the tau is a constant and the beta is the variable. So what I'm going to change is t by beta. Okay, so beta is equal to t minus tau. Okay, differential of t is equal to differential of beta, because tau is a constant for this integral. Okay, so this integral, I don't change it. I'm going to make it 0 to infinite f of tau, integral from exponential minus s tau plus beta is equal to t minus st, alright? And then g of beta, but beta is t minus tau, differential of beta is equal to differential of t, and then differential of tau. Now be careful here, because here the limits, this is beta equal to 0, beta equal to infinite. But now it is integral respect to the time, so we cannot place just 0 and infinite because it's a different variable. Okay, what we have to do is to make the evaluation. What is the value of beta when what is the value of t when beta is equal to 0? When beta is equal to 0, so this is tau, and when beta is equal to infinite, tau plus infinite is still infinite. Okay. Okay, now, so we come up with this integral. Now, the region has changed. So it is now tau, and now this is not beta, this is t, alright? Okay, so now it is from 0 to infinity in tau, from here to here, all the way up, but here is from t equal to tau to infinite. Now t equal to tau, which is this, y equal to x to infinite. Now this integral from 0 to infinite is vertically in the tau direction, and differential of t is in the x direction. So it is from t equal to tau to infinite, from here to infinite. So that is the region. So we have changed the first quadrant, which was the region. Now this is the region because we changed this variable. We changed the beta by the t. Okay. So I think it's pretty heavy, but I hope you are still with me. Okay, now let's make another change here. I'm going to write this integral. I'm going to introduce the f of tau, integral from 0 to infinite, integral from t equal to tau to infinite, with t equal to infinite. Now this is tau equal to 0 to tau equal to infinite, from 0 to infinite, and then from the y equal to x to infinite, alright? Exponential minus st f of tau g of t minus tau differential of t differential of tau. What I'm going to do is a change in the integral order. So here first is the integral respect to the time, and then respect to the tau. What I'm going to do is a change. I'm going to make the integral respect to the tau first, and then respect to the time. Now, if we do that change in the integral, what is inside, it doesn't affect it. It's not affected. What it is affected is the variables here and the region. So instead of going from 0 to infinite and then from here to infinite, what I'm going to do is first from here to here, and then from 0 to the, well, invert the integration order. Okay, so what I'm going to do is first the integral respect to the time, and then the integral respect to the tau. As you can see here, we just flip this, differential of tau, differential of t. So inside, we don't change anything, exponential minus st, and f of tau, g of t minus tau. Again, we don't modify this inside, what we are going to change is the integration order. Now, in the time, it is going to be from 0 to infinite, and then from 0 to tau equal to t, from 0 to tau equal to t, tau equal to t. So here is just t. So again, in the previous integral, it was from 0 to infinite, and from t equal to tau to infinite. Now it's going to be from 0 to infinite, and from the floor to the t equal to tau. Okay, so this is the result. Okay, now because the first integral is respect to the tau, then the exponential of minus st can be taken outside because it doesn't have taus here. Okay, so what we can do here is the integral from 0 to infinite, exponential minus st, and then the integral from 0 to t, f of tau, g of t minus tau, differential of tau, and then differential of t. Now here comes the rules, engineers. This part here, we have seen that before. This is actually the definition of the convolution, if you remember. So this is equal to, So if that is the definition of convolution, then is equal to the integral from 0 to infinite exponential minus st, and then here is the definition of convolution, so it's going to be f of t convolution with g of t, differential of t. Now, have you seen this before? It is actually the definition of the Laplace transform from 0 to infinite exponential minus st, and then here this is the argument. So this is actually the Laplace transform of the convolution of f of t with g of t, the definition. Now, from where this comes from, we started from here and we finished here. So we started with the f of s times g of s, and that is equal to the Laplace transform of f of t convolution with g of t. Okay, engineers, so the previous example was not we were not lucky. It is actually true. The Laplace transform of the convolution is just the multiplication of each one of them. Right? Okay, see you on the next video. We are going to solve a problem that contains a convolution inside the differential equation.